world champ of the evening. Today, இன்னைக்கு Give me a second though. Give me a second. Lead code backend. I need to check a lot of stuff. So that was my folder. So when was the first lead code ever? I mean, stream ever? So this was August. So it's been, I skipped 17, man, I skipped like 30 days of like actual work. I think some of it is like warranted because, let's do some quick math. I think, fuck. Minus 2, minus 2, minus 4, minus 6, minus 8, okay. Minus 16. I think 16 days are warranted, but yeah, 16 days are warranted, but fuck, man. I need to like match my numbers. So I got 6 views on this one. That was my highest viewed. I think this one is gonna be my highest viewed from now on. I don't know. What the fuck? 20 people watched it? That's crazy. Twenty people watched it. Crazy. Yeah, I don't really like check all of this stuff. It's funny, so cute. Now it's high production. You know, we got a thumbnail going on. Beautiful looking thumbnail. Bro, I would actually click on this, you know? If I saw this out in the wild, looks like a clickable link, if you ask me. I tried playing like Resident Evil. I got like so scared. Such a scary.
To be done with this babysitting.
Scary game, man. It's a scary. It's all choppy. I'm gonna need to like figure how to like do it properly. Well, where are you guys in this view? I know I look good, but I need to change the layout. It's all choppy. I'm gonna need to like figure how to like do it properly. Well, where are you guys in this view? I know I look good, but I need to change the layout. Going on. I got like so scared. I'm checking my profile view. Bro. It's funny, so cute. Now it's high production, you know, we got a 20 people watched it. Crazy. This one. Okay, I'm just gonna jump right into it. So you could skip all of that rambling. And we're gonna jump right into one hour of intense focus. Let's go. I'm gonna do some sliding window binary search. I did this one. I was using a while loop, and let me think. I was using a while loop, and if it's like smaller than this thing, and I was traversing to the middle, so I had a middle. No middle. Okay. So okay, we have middle in here. So what I did was, it was a while loop. So this is the array, left pointer, right pointer, and while this condition, the condition is when the left is more than or equal, when the left side is more than or equal, I need to do this function where I need to take the middle and compare it to the left side. I need to take the target value and compare it to the middle. If it's bigger meaning it's in this side, the middle value, I'm gonna do this sort of thing. The middle value, if it's bigger, I need to get this pointer one step closer, and if it's one step closer, else if it's the same thing, then return M. So I'm gonna get this middle now. Okay, perfect. Binary search. Voila, bro. Voila. Understand it. See, that's the thing. Like, we have an easy problem here. We're jumping straight into like a difficult one. Like, why does it have to be a binary search? You're given a target matrix. Each row matrix is sorted on decreasing order. Decreasing. Okay. Even the columns are like in decreasing order. If you think about it, the columns are all in decreasing order. Cool. Return true if target exists in the matrix, or false. Can you write an N of? Okay, I need to do it in binary search. Hence the time specification. Because when I do it in a normal array search or with a for loop or something, it's gonna take N of O of N time, right? You wouldn't take log of this. This is actually a smaller number than O of N log. That's the point. Okay, let's actually like look into the matrix, and we need to find 10. As you can see, the 10 is over here, and luckily for us, everything is in ascending order, normal order. But I wonder what happens if, let's say, instead of 10 here, there is 7, right? I mean, that's a bad example. Instead of like 14 here, there's like, I don't know, 9. What would happen? So I don't think that's the case in this particular question. So I'm going to move on to where everything is like sorted already. So in the case of, it's instead of like saying while left pointer and right pointer, I need to be more specific and be like, while left pointer in this, while the left pointer and right pointer, if it's bigger than this, move on to the next array, which I think it'll make the process a little bit faster. I mean, a little bit more, because it's not log of m. If we go back to the question, the previous question, we could clearly see this is log of n. Yeah, it's two arrays. We're traversing through multiple arrays. That's why it takes m into n. That's the thing with space and time complexity. So the way that I would go about doing this is, it's pretty simple. I think I need to traverse through. So before I touch the code, let's see. Yeah. Which company? Okay, I need to. I swear. Okay, so I'm gonna name the firstly I'm gonna name the left pointer and right pointer. Instead of naming it like left pointer being here, right pointer being here, I think I'm gonna do it in a way that's a little bit more programmatic, where I have to do it in a for loop, I think. Let's give it a try. Let's look at the solutions, obviously, because I'm not really like doing this for real.
Hey everyone, welcome back, and let's write some more neat code today. So
I need to take a piss before that. I'm gonna fill this water bottle too.
today let's solve search a 2D matrix. And I really like this problem because it's not one of those problems that you need a fancy trick for. You can actually solve this problem just by using logic. So we are tasked with creating an efficient algorithm for searching for a single value in an m by n matrix. The matrix has two properties. In every single row, the integers are sorted from left to right, and the first integer of each row, for example, this 10, is always going to be greater than the last integer of the previous row. So greater than this one.
Yeah.
So in other words, we know that each row is sorted, and then the next row is going to be greater than that. So technically, each value in total throughout the entire matrix is going to be in sorted order. So that's pretty good. In this example, we were given a target 3, so if we search for the target, we will find it right here. So then we can return true that it does exist. If it does not exist, then we simply return false. So how can we solve this problem? The key word here is create an efficient algorithm. What would be the brute force? Of course, we could do an algorithm O of m by n, basically by searching every single value in the input array, right? That's a pretty easy algorithm to do on a two-dimensional matrix, but can we do better? Of course we can, because they gave us a couple properties that this matrix has some sorting already applied to it. Assume that we just had a single row, like forget that we had a matrix. If we just had a single row like this one, and we know it's in sorted order, do you know an algorithm that can search for a target value in a sorted array? I know of one called binary search, right? And how efficient is binary search? Well, let's say the size of this array is n. We could do a binary search in log n time, right? But of course, we know that we actually have m different rows, right? So let's say we ran a binary search on every single row until we found the input target value, right? What would the time complexity be? Well, log n multiplied by m is going to give us a solution like that. So that's using the first property, knowing that each row's integers are sorted. And this is a pretty good solution, but can we do even better than this? I'll give you a hint. We're definitely going to have to use this second property that they told us. Each row itself is actually in sorted order, as in we know that the values in this row are going to be smaller than all of the values in this row, and all of the values in this row are going to be smaller than all of the values in this row. So can we use that property to, instead of searching through every one of these m rows, maybe we can actually do a binary search just to figure out which one of these rows to search in the first place? Because for example, if we're looking for a target value 3, let's take a look at this row. This row could have any values between 10, which is the lower bound, and between 20. So obviously the target value 3 is not going to fall within that range between 10 and 20, right? So then the question is, okay, if the target value is definitely not in this row, we can cross this row out. But then which direction are we going to go? Are we going to look at the row above it, or are we going to look at the row below it? Of course we would want to look at the one above, right? Because above, the top row is going to have smaller values than the bottom row, right? So when we cross this row out, we can also say that, let's cross this row out too, because of course this row is going to have greater values. That's how the binary search is going to work to even figure out which one of these m rows we're going to need to search, right? So we can reduce, instead of m, we can do a log m by running binary search. After we've ran that log,
you're going to do it twice. That's the premise. 74.
Function, which provides the probability of the next state and reward given the current state and action. Our goal.
Whoa. Well, actually, shut up.
m search, then we know, okay, this is the row that we have to do our second binary search on. So after we're done with that, we're going to do another binary search. So that's once we get, so of course, out these values. Of course, let's get into the code. Do that pretty easily because we know for sure that the matrix is.
What? Rows and columns? Why? If the rows...
Always going to be non-empty. And now we're going to do the first binary search. We're going to look for the row that we need to find. So I'm going to have 2 pointers, one for the top row and one for the bottom row. Top row is 0. The bottom row is going to be the number of rows minus 1. So now we're just going to continue to...
Why 0 columns? Nigga, column's supposed to be. Why is it 0?
Do the binary search until we can either find the target row or we figure out that the target row does not even exist in the binary search. So one case is that the target value is even greater than the largest value in this row. So let's go to that row. Okay, first, before I do that, let me actually compute the row. So we want the middle row. In this case, we'll take the top and bottom and divide it by 2. That's kind of how binary search usually goes, right? So, and then we have that row. So in our matrix, we're going to look at that row and we're going to look at the rightmost value. In Python, you can do that with -1, but we could also just do number of rows minus or our target value every single. Let's compute the middle point. We can do that by.
Yeah, this is too much. I don't think I can do it. Yeah, like a lot of matrix. Matrix. I YouTubed it. So. Oh, I wanna fuck this. What? Linked list? What are you saying, man? Linked list? Trees? Should I do a trees one? Invert a binary tree? Binary tree? I've never done a binary tree though. So many things. Oh yeah, using alphanumerical. Like, what the fuck? What am I supposed to do? Nah, I ain't doing this, G. Why is this so tough? It shouldn't be this way. Sliding window, why not? Output. Supposed to be the easy one. Supposed to be the easy one. Sliding window maximum. I'm gonna attempt this. You're given an array of integer nums and integer k. There is a sliding window size k that starts in the left edge of the array. The sliding window one position to the right until it reaches to the right edge of the array. Return a list that contains maximum elements in the window each step. What? What the fuck am I looking at? Let's do the minimum win. I don't even know, bro. Don't even know what I'm looking at. It's the easy questions that I need to like know, like it's my back of my hand. Let's do all the easy questions in this thing. Invert a binary tree. Let's go. So root optional tree load. Oh fuck. Fuck.
Then we can return null. We don't have. Hey everyone, welcome back, and let's write some.
22. I'll do that in a minute, but I need to build a habit on doing this. Okay.
Some more neat code today. So today let's solve a pretty easy and popular question: invert binary search tree. So all they tell us to do is invert a binary tree. And what exactly does that mean? So let's say that this is our initial tree. To invert it is basically what you can tell in the output, right? So the root stayed the same, but you can see it's two children, which were left child 2, right child 7, were swapped, right? So 7 is now on the cursive definition. So take a look at this, but now 3 is on the left and here 3. What we're saying, so in invert cursive post order. So this problem would probably be a lot more annoying if it were iterative, but luckily we can do it recursively. So we can first check the base case. So if the root is null, then we can return null.
If not root. What does not root mean? What the?
Return null. We don't have to continue. Otherwise, what we're going to do is swap the children. So we're going to save the left value.
Why don't you pin that, you motherfucker? What is the solution that you gave? Staircase. That is wrong. Indentation error, fuck's sake. Cash rules everything around me. Queen, get the money. Dollar, dollar bill, yo. What that mean, nigga? If not root. Oh, wrong question. Interesting. If not root, return none. If it is not root, so return none. Root dot left, root dot right. Okay, self. Okay. Return root. I'm just swapping it. If it is a not root, return none. Okay. Okay, if it is a not root, return none. Okay. If it is a not in root, return none. Okay. I'm just swapping it. But what if he has like a lot of children? Yeah, what happens to this? Else. That is the else. Why is it not iterative? I kind of get it, but it's like, why is it not iterative? It should like, okay, this is equal to that, that is equal to this. Cool. But how is these changed? Oh, is it auto iterative? Does it like iterate automatically on everything?
Hey guys, Greg here. Let's solve invert binary tree, leak code number
I got
226.
Greg.
So we are given the root of a binary
I'm
tree,
Greg.
and we want to invert the tree and also return that tree's root.
I'll
Okay,
beat
so
you
what
up.
inverting
I'm
is,
joking.
it's
I'm
basically the
joking.
process of turning it from the left tree into the
I'm actually
right tree.
Greg.
So as you can see, the root's
I'm a
the
nice
same.
guy.
That's always going to be true. But then what's on the left here is a 2, but in the inverted tree, it's actually what's on the right is a 2. And again, over here on the left, what's on the right is a 7, but over here in the new one, it's the left is the 7. So basically, you have the left and the right arms are going to swap. For this 2 here, we'll notice that over here its left is 1, but over here its right is 1, and over here its right is 3, and over here its left is 3. Okay, so it's basically for every single node that you have here, you swap its left and right arms. Okay, and they have an even simpler example right here. If you have just 2 and then 1 and 3, it's just 2 and 3 and 1. And the third example shows we're actually allowed to have 0 nodes in the tree, and if you have 0 nodes in the tree, it doesn't actually mean an empty list here. That's just a way to represent that the tree is null, and so you would also return null in that case. Okay, so if we were given this root here, we'd be given this node. It has a left and a right. Now the first thing you pipe to
Nigga, I know that.
it's left. We visit this left node over here. We would swap it root. So this is our big 2. We're gonna really help the problem arms, and then we just need to do this recursively. So if we did it for root, we swapped its arms, we just need to go down and do it for both its left and right. So then we actually need to do self here because it's in a class. It's kind of irritating, just a silly Python thing. So we do self.invert tree on the root.left, and we would also do self.invert tree on the root.
Root dot left, root dot right. Okay. Will this pass? Fuck. Where is it?
Dot right. So we do it on the left, we do it on the right, then he's going to do the same thing all the way down, and then at this point we are done inverting the entire tree, and so we can actually return the original root, because that is what
How do I know it's done recursively? I don't get it.
the question wants here is to return the new binary tree's root. Okay, so the time complexity of this, well, this is basically
I kind of get it, but I don't. You know, let me try to do it myself. So basically, if it is not root, there's like no root. I need to return none, and else self dot. I need to do it recursively. I don't know how to do it, but right comma self dot. I don't need this shit, honestly. I actually need it. I actually need it. It's a stand. It's a laptop stand. Y'all, you peasants wouldn't get it. It's alright, fine. The alphas only get it. Okay. Is equal to. I'm getting invert self dot. Bro, literally the same. You guys just hate me. You guys are just like brown phobic. Because what do you mean? Like I literally did the same thing. I literally like copy pasted it. I copy pasted it and it's like still okay. I need to return root, of course. Of course, bro. Why is it iterative anyway? Return. So what's the solution now? So I'm getting. Why am I getting none? Okay, this makes sense. So I need to go return root and to return that actual root. And now I'll get the what? My output, expected output. Well, actually, yeah, I swapped it. Yeah. Yeah, I think I swapped it. What's the issue? What's the issue here? What's the issue here? I swapped it. Fuck's sake. I have to copy this. Go here. Fuck. So, use the self dot shit. I'm going to do another tree. The depth of define the number along the okay depth. I need to find the depth. Null. Um, 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 2, 3, null, 4. I need to find the depth. Fuck's sake. How do I find the depth? So depth is 3. I need to go. I have no idea.
Hey everyone, welcome back, and let's write some more neat code today. So
Maximum depth. Actually, let's 40 minutes. Give me a second. I'm gonna take another piss break. I'm gonna think about it while I take a piss.
Today let's solve maximum depth of a binary tree, and the main reason I'm solving this today is just for the sake of completion. We have solved harder tree problems before, but this one is on the blind 75 list, so I do want to solve this problem today. And this problem actually has multiple ways to solve it, so I do think it's a good problem to understand of like the fundamentals on tree traversals. We can do it 3 different ways, and I'm actually going to show the 3 different ways. There might even be more than 3, but I'm going to show you the 3 main ways. Basically recursive depth first search, iterative depth first search, basically depth first search without using recursion, and of course another way is going to be breadth first search. So I'm going to be showing all 3 today. So the problem is pretty simple. We're given a root binary tree and we want to return its maximum depth, and the maximum depth is defined as being the longest path from the root to one of the one of the leaf nodes, and basically along that path we're counting the number of nodes. So in this case you can see we have 2 paths that are of the same length. So from the root down to here we have 3 nodes, from the root down to here we have 3 nodes as well. So those are the 2 leaf nodes we have here. We also have a leaf node on the left side, but clearly we see that there's only 2 nodes in this path. So out of all those paths, what's the max length? Of course it's 3, so you can see that that's what our output is going to be in this problem. So the simplest way to solve this problem is recursive depth first search. Now, what's the base case? We're using recursion, so first let's think of the base case. Obviously, if we had just an empty tree, right? Like what if this was our tree? What are we going to return? Of course 0, right? The max depth of an empty tree is just 0. What about if we just had 1 node and no children, right? Okay, we do this recursively, so we'd get to the first node, right? We'd say, okay, we at least have 1 node. Then we'd say, okay, let's just find the max of the left subtree and the max of the right subtree. Both.
Give me a second. Yeah,
those are going to return 0, right? So once we get back to the root, what are we going to say? We're going to say, okay, the left and right subtree were 0, so the maximum of the left and right subtree is also 0. So what we're going to return from the perspective of this root node is just going to be 1 plus the max of the left and right results. Basically the max of the left and right subtrees, in which case it was both 0. So of course in this problem we're going to return 1 as the max depth. Now let's look at this more general example that they gave us. So obviously we're going to do the same thing. We're going to get to the root, say, okay, we found at least 1 node, so the depth is at least 1, and then we're going to return the max of the left and right subtrees plus 1. And why are we doing it this way? Well, you can see that we found this node, but now we have sub-problems, right? We need to know what's the max path, what's the max depth, and we'll have to search the left subtree, and we'll have to search the right subtree. So we're not even considering this node anymore. We're doing recursion. We're looking at the sub-problem. What's the max depth of this left subtree? Well, of course, it's just a node, a single node with no children, so of course the max depth is going to be 1. Similarly, let's do the right subtree, and so again, this is going to be our recursive case, right? We have 1 node, and from then this node's perspective, we're going to run recursion again. We're going to look at the left subtree and the right subtree, both of which are going to return 1. So then, of course, from this node's perspective, we're going to return 2. The max depth of this subtree is 2. The max depth of the left subtree is 1. So now, when we get back up here, we're saying, okay, from the perspective of this node, we're going to return 1 plus the max of left and right. The max is clearly 2. So from this node's perspective, we're going to return 3. The max depth is 3. So let's code this up recursively. It's literally just going to be this line that I just wrote and the base case. And since we are traversing the entire tree, the time complexity is going to be big O of n. The memory complexity is just going to be the height of the tree, which also could be worst case big O of n if it's not a bound.
Can't you do length of? Probably not.
Balanced binary tree. So with recursion, we always want to take care of the base case side of the function. In Python, you have to say self.maxDepth, and then run that on the left subtree, and also run it on the right subtree. Now, to make this line shorter, I could actually store the result of both of these function calls in variables, but I think this one-liner is pretty much good enough. So we're just taking the result of both of these function calls, figuring out what's the max of it. So what's the max subtree's depth of both of the subtrees, and then just adding 1 to it, because we know that the current node, the current root node that we're traversing, is definitely not null. So this calculation will work out. Let's submit it. And of course, I'm showing that I can't even solve easy problems, so it's not called node, it's actually called root. Hopefully you were able to catch that. But yeah, so this is the entire problem. But what if you're an interviewer, or what if you just want to do this for learning purposes? You want to solve this problem without recursion. Well, there's two ways to do it: iterative depth first search or iterative breadth first search, and I'm going to show you both of those right now. Now, there's not a lot of benefits to using breadth first search on this problem compared to just doing DFS recursively, mainly that you just don't have to do recursion at all. The time complexity is still going to be the same, the memory complexity is still going to be the same, but let's still do this for learning purposes. So breadth first search on a tree is basically level order traversal. We're traversing each level by level until we get to the end or the last level, and then we can't continue anymore. So you can kind of see how breadth first search is a pretty intuitive way to find the max depth, right? We're basically counting the number of levels we have. So here we see, okay, we have one level. Next we see we have two levels. Oh, this is the third level, and we can't go any lower. So what's the number of levels that we had? We had 3. That's the number of levels is basically going to be the same as the max depth. So now the only problem is, how are we actually going to code this up? Now, typically BFS involves a queue or a deck, a DQ, or however you call it. And so the way it's going to work is the queue is initially just going to have the root value. So I'm going to kind of represent this array. 15 is the first one. Let's pop it. Let's get rid of it. Stack data structure, because we're basically going to be emulating the call stack, the recursive call stack, right?
So this is the recursive and
iterative depth first search solution, basically depth first search without using recursion. So now we're going to do iterative depth first search, and we're going to be needing a stack data structure because we're basically going to be
fuck no. I kind of get it, but I don't. I'm going to move on to the next one. Diameter of a binary tree. Okay, this is going to be a breadth first search, I think. Okay, this is going to be a breadth first search. I can tell.
Data structures and algorithms,
Bro, just don't like this guy. Okay, this is going to be a... Where is... I literally finished it, mate. Literally done. Okay, who cares? Get out.
Hey everyone, welcome back, and let's write some more neat code. So today let's solve diameter of binary tree. We're given the root of a binary tree, and we want to return the length of the diameter of the tree, which is defined as being the longest path from a particular node. So in this case, it would basically be the longest path on the left side, which could either be this part or this part. Both of those are of length 2. I'm getting that calculation because 2 is the number of edges on that side for the longest path. On the right side, we just have one edge, so that's 1. So the diameter through the root would be 2 plus 1, which is 3. But keep in mind that the longest path might not necessarily run through the root. So let's look at a counterexample. With this tree, if we try to calculate the diameter through the root, on the left side we have nothing, so that's a 0. On the right side we have 3. That's the longest path. You could take multiple different paths, but all of them are going to be of length 3, so the diameter from here is 3. But consider the node over here. Length on the left side is 2, and length on the right side is 2. So total is 4. That's the diameter of this tree. Now, I want to mention to you that this problem is actually closer to a medium problem than an easy problem. Why exactly is that? Because the solution initially seems pretty obvious, right? To get the result, we can just try to calculate that diameter through every single node in the tree. How do you do that? Well, just like I did, get the longest path on the left and the longest path on the right and add them together, aka sort of like the height on the left side and the height on the right side. Generally, we do this recursively with some kind of DFS algorithm.
Too much. If it's like too difficult, I'm not doing it. I'm pushing out. If it's too difficult, same tree, subtree to another tree. Given the binary tree, return true if the height is balanced, false if otherwise. The height balance binary defined as a binary tree in which the left and right subtrees are in every node differ by the height in no more than less than 1. Okay.
Hey everyone, welcome back, and let's write some more neat code today. So
I never wanted that, so fuck off.
A depth first
today
search.
let's solve the problem balanced binary tree.
Fuck.
tree. We're given a binary tree and we want to determine if it is height balanced. What exactly do they mean by height balanced? Well, it's defined by saying that for every single node in the tree, if we take the left and right subtrees of this node, the heights of these left and right subtrees will differ by at most 1. So in here you can see, taking a look at the root node, it has a left subtree. What's the height of this left subtree? Let's call it 1, right? Because there's one node in the left subtree. What about the right subtree? What's the height of this right subtree? Well, it's 2, right? We can determine that just by looking at it. So then the left subtree has a height of 1, the right subtree has a height of 2. The difference is at most 1, right? Because if we take the absolute value of the difference, we get 1. So we'll say the difference is 1. So we just did that for the root node, but we have to do that for every single node to make sure that the left and right subtrees of every single node differ by at most 1. And just to show you a counterexample, so this is kind of a badly drawn tree, but take a look at the root node, right? If we take a look at the left tree over here, the height is 3. If we take a look at the right subtree, the height is 3. So the difference is 0, which fits into our criteria. So from the root node, the left subtree and the right subtree are balanced. But if we take a look at, let's say, this node, right, we take a look at its left subtree, which is empty, right? So that has a height of 0. The right subtree has a height of 2. So in that case, the difference is 2 minus 0, which is 2, right? Positive 2, which is greater than 1. So just because from here, taking a look at the root node, the left and right subtrees are balanced, doesn't mean that that's going to be true for every single node, because we just looked at this node, the left and right subtrees were not balanced. How can we solve this efficiently? Let me first show you kind of a naive approach, and then we'll see how we can actually optimize that. So if we were asking naively, right, the first question we're asking is, from the root node, are the left and right subtrees balanced? How do we even determine that? Well, do you agree that we could probably do a recursive DFS on the left subtree to determine the height of the left subtree, do a recursive DFS on the right subtree to determine the height of this subtree, and then we could compare those and make sure that the difference is less than or equal to 1. Do you agree that we could do that? Probably, right? I'll explain more details in the code, but for now, let's just assume we can do that. We start from the root, we run a DFS on the left and on the right. That means we go through every single node in the tree, so we just did an O of n operation, right? And we were able to determine, okay, from the root node, yes, it is balanced, but we're not done yet, right? Now we have to continue to ask that question for every single node, right? So the next question we're going to ask is, suppose on the left subtree, right? From the left subtree, are the left and right subtrees from this node also balanced? And of course, they're both 0, so we determine that they are. And then we'll have to recursively go to the right subtree. From here, we're going to ask, are the left and right subtrees balanced? Yes, they are, but we'll recursively have to continue. We'll have to do that from this node, and then we'll have to do that from this node. Since we're running a recursive DFS on every single subtree on this root tree, we're going to have to do it basically an O of n operation each time we ask that question. Is it balanced from here? Is it balanced from here? Is it balanced from here? And we could have a really big tree, and we have to do an O of n operation each time. O of n is the number of nodes in the tree, and if we have to do this n operation n times, we're going to get a time complexity of O of n squared. So now the question is, can we do better than that? Is there any repeated work? And I'll show you that yes, there is repeated work, and it basically can be eliminated by asking the question in a different order. What I mean by that is, instead of first asking if the entire tree is balanced from the root node, right? That's the first question we ask. Is it balanced starting from here? Instead of asking that, we do this bottom up. We recursively, instead of asking it from here, we're going to check, okay, is this entire right subtree balanced? Before we do that, we're going to ask, is this entire subtree balanced? And we're going to keep going lower and lower until we get to the base case. Once we get to the base case, then we're going to go back up, and I'll show you how that's actually going to end up eliminating the repeated work. If we do it in this order, we'll only have to visit each node at most 1 time, which will ensure the overall time complexity is going to be big O of n rather than n squared. Okay, so when we get to the root, before we check if it's balanced from here, we're going to check if it's balanced from this right subtree. That makes sense so far. And then before we ask from this position, we're going to ask, is it balanced from this leaf node, right? And now we can't really go any lower because this node doesn't actually have any children, so of course its subtrees are going to be balanced. But now we're good, right? We determine, okay, this from this node, yes, the left and right subtrees are balanced, right? And then we pop back up, suppose, and then we also want to make sure that this down and revisit the entire right subtree and the entire left subtree again. We already have the height of this tree, we already have the height of subtree. So node as well, value, which will be balanced. If we find even one subtree that's not, main thing is we're going to do this recursively. Why can't I just use this outer function to do it? Because
Okay, I think I'm done. I'm gonna do some research. Find the best path for submissions. Oh, now we're talking. Modeling for, it's good for, fuck sake, can I get a pen? Can a nigga get a proper pen, please? Fuck you. Backtracking. Okay, I think I'm done.